which is called work. All right. So I'm going to present work. So some of you may have seen some physics before. You may have seen work before. It's possible that I'm going to present work in a way, well, I'm going to present work in a way that makes a lot of sense relative to how we are thinking about derivatives and integrals. It may be slightly different than what you've seen before, but the great thing about physics is that it's all the same. So for our class, you only need to think about work in this very nice and what I think will be straightforward way. So here we go. So what is work? Work is just the amount of energy expended. So things like lifting an object or moving from here to there, all these things in physics require something that's called work. Force is the amount of work per unit of distance. So for example, if I were to push this desk from here to there, then I'd be applying a force in order to move the desk, and I'd be applying it over a certain distance from here to there. So the force is what I'm applying, and the work is done during my entire trip, if you like. Okay, so that's a very simple way to think of work. All right, and once again, we have this issue of units. The American units are the ones that we're used to, but they're very confusing, so I'm not going to mention them until later. So we're going to use the metric units. So work is measured in joules, and force is measured in joules per meter. And joules per meter is also called newtons. Okay. So now just from the units that I've written down here, sorry, one sec. Okay. So just from the units that I've written down here, can you guess which is the derivative of which? Right. Right. So there's joules and joules per meter. So clearly joules per meter is the rate. So force is the derivative of work. So there you go. And so right now we're going to think of these as functions of distance. And I'm going to make the choice to say that our variable is x, and x is going to represent the distance traveled. Okay. So obviously, since the derivative of work is force, then we also know it the other way around. The integral of force is work. Okay. So now before we get to the calculus case, let's take a moment to get used to the physics. So again, let's talk about like simple linear case. So again, I'm going to push my desk, and that requires a force of 7 Newton. 7. You know what? I'll actually write it out in the nice way, joules per meter. Okay. How much work is done to push the desk from the 1 meter mark to the 6 meter mark? Yeah. Okay. So if you know physics, you've already done this and you can do this immediately. If you don't know physics, you have to think about what this means. Okay. So the simple way to do this is simply to say that if it's just the linear case, well, we know it's like rate times the other units equals the total amount. So we're sort of, instead of rate times time equals distance, we're generalizing always. So it's rate times your variable equals the amount. So the rate is 7, and the variable I'm working with is distance, but what do we need to multiply by? Right. So we just talked about this. So I need to multiply travel. Well, the distance traveled is, I started at 1 and I finished at 6. So it should be 6 minus 1, which obviously is going to be 5. And that's going to be the work. So this is going to be 35 joules. Okay. So notice that work equals force times the change in distance, which we're writing delta x.
This was the best physics. This is like the best physics class. We've never understood this in physics.
Right. Well, here you go. Okay. So if that's how we write it, so that's one way to write it in the linear case. Now let's think about it this way. If the amount of work done by a tow truck is W equals 20x, how much work is done after 0 meters? So what do? You just plug it in, because we're being asked to find the work, and what do we have a formula for? Work. Super duper. So you get W of 0 is just going to be 0. And then we also want W of 5, which is clearly going to be 100. And 100 what? What are we measuring? Work. So this is joules. Joules and joules. Now, what is the force of the tow truck?
Take the derivative of it.
Yeah. 20 joules per meter, or newtons. Okay, so now obviously the sophisticated way to say we're going to find the force is just take the derivative of work. But the nice way to think about it, because it's just the linear case, is to know that it's work equals force times distance. But of course you can only do that in the linear case. So the force is 20. Okay, now we're going to kick this up to calculus. Suppose a magnet exerts a force of F equals x to the negative 2 joules per meter. How much work is done moving an object from 1 meter I'm going to change this around, excuse me. Actually, let's just leave it like that. Okay. How much work is done moving an object from 1 meter to 4 meters? Yeah. So we want to find the work. How do we find the work? Yeah. Right. So the old naive way was that it was force times the change in distance. But of course now we know we're doing calculus. So this is going to be the integral of force dx. And in this case it's the integral from where to where? From 1 to 4. Okay. So I want to mention something remind you something that I mentioned before, which is for context problems it's going to be helpful to get used to just moving lots of different letters around. So in this case, I just wrote down f. Now I could also have written down f of x. It's helpful to be able to think of it either way. But again, notice that when I take the integral of f, I'm not going to get f squared over 2. F is some function. And I'm just writing it down symbolically by saying f, it's my force. So this is the integral from 1 to 4 of x to the negative 2 dx. So this is now, need some more room. What does this give me? X to the negative 1 over negative 1. I can just simplify that by putting a negative in front. Okay. And this goes from 1 to 4. So plug in force, you get negative 4 to the negative 1 minus negative 1 to the negative 1. So what does this give? So that's negative a quarter plus 1 over 1. So this is just 3/4. I'm just going to write 0.75 joules. Physicists use J for joules. And there you go. Okay.
You're better than our previous physics professor.
It happens. Okay. So does this make sense? Okay. So everything should fall together once you realize the key relationship, which in terms of mathematics is, what's the relationship between work and force?
Distance?
What's the relationship between work and force?
The derivative.
That work is the derivative. That force is the derivative of work.
Right.
Force is the derivative.
Force is a derivative of work. And to be specific, the derivative with respect to distance. But yes. When you integrate x to the negative 2, it's a power rule, so you add 1 to the exponent. Negative 2 plus 1 is negative 1. Okay. So in this problem, I gave you the force function, and I just made up something that I liked. It turns out that in a lot of different situations, the force function follows some kind of special rule. And I'm going to show you some of those. Now, before I do this, I just want you to know this is not a physics class. I don't expect you to memorize any physics formulas. To the extent that you ever have to use any of these, I'll give them to you. But a lot of people in here are also interested in physics, so it's always nice to see what this has to do to how this applies to fields of science. So let's go. Hooke's law for springs. F equals kx. Okay, so let's say that we have a spring, and I'm just going to tell you that the spring constant k is and k is called the spring constant. It's a constant for springs. Okay, so k is 25. How much work is done as it moves the object from 2 meters to 15 meters? So we're trying to find work. So work equals what? Right. Okay. And also, I'm sorry, I want to, well, okay, so yes. Okay, so the integral from 2 to 15. Right. So just symbolically, it's just f dx, right? But so let's write that out properly. 2 to 15 of
25.
Right. And then the rest is just really, really easy calculus. Okay, so 25x squared over 2 is going to be 12.5 x squared from 2 to 15, and then just plug it in. Okay. Okay. Oh, and I don't want to make the same mistake that is typical, so I want to be precise. Now, I just wrote work equals. Now, that's true informally, but formally, we're doing something very specific. Which work are we finding? The work from 2 to 15. Now, how do we write that down in math?
Work of 15 minus work of 2.
Yeah. Okay. So, if you understand that, I'm sorry? Well, what is work delta x? What does that mean? It's not clear. Yeah, the way to write that down is like this. Yeah. Question?
I missed where you got the 25x
Yeah? Did anybody do this on the calculator, figure out what it is? Okay. So it's going to be something minus 50.
The total answer is 2,762.5.
If you say so. Okay. And that's 2,762.5 what? Bananas?
No, joules.
Joules. Okay. Okay. So here, so another spring problem. Suppose a spring exerts a force of 30 joules per meter when extended 6 meters. How much work is done extending it from 6 to 12 meters? All right.
So Kx is equal to 30.
Okay. So what piece of information is missing here?
From 0 to 6.
K.
There's no K. So what do you think you're going to have to do? You have to find K. Now, what formula do we know that involves K?
F equals Kx.
Yeah.
We can rewrite it at that.
So F equals Kx. Well, what piece of information do we have?
df and dx.
Right. So and the value for F is
30.
30. And what else do we know?
X 6.
When X is 6. So what's K?
5.
You solve for K and you find that it's 5. Let me
If we didn't know the 6, can we theoretically rewrite this in terms of K and then integrate?
Yeah.
And then we'll find K.
No, you can't find K later. If you didn't have this fact, you wouldn't be able to find K, and K would just carry through as some constants.
Okay.
You can do it that way, but it's just less interesting. It's less concrete, I'll say. Okay. So now we know this. So now we actually know the force formula in this case. So now we know that the force equals 5x, and now you just continue to do the problem like regular. So how much work is done?
50 degrees.
So I'll say work at 12 minus work at 6. So that's the amount of work done equals. So it's going to be 5x squared over 2. I like to use decimals just because, I don't know, from 6 to 12.
270.
And one's, okay.
Yes.
So this is
360.
360 minus
minus 90.
So you get 270 joules. Okay. Okay. So is that straight? Oh, Steve, is that straight? Yeah. See, Wilson, is that straight? Okay. Next law of physics. Law of gravitation between two objects. So when you have two objects, the force, which is I guess the acceleration due to gravity between them, is k, which is again some universal constant, times m1 times m2, which is the mass of the first object and the mass of the second object, divided by x squared. X is the distance between them. Okay, so two objects are currently 1,000 meters apart, exerting a force of 5 newtons. How much work must be done to move them to 5,000 meters apart? So how do you do that? So we're trying to find work. So what is it that we're going to do? Well, what's the relationship between work and force? Right. Force is the derivative of work. Therefore, if we're trying to find work, you have to do the integral of f dx. That's the general rule. Now, what do we have to do specifically in this problem? The integral of what? Oh, shoot. I'm sorry. I skipped a whole step. Apologies. Okay. The problem is our function f is filled with all these constants that I haven't told you what they are. So what are we going to have to do? Yeah, we got to find them. So sorry, let's kick that to the curb for a second. Okay. So how do we do this? Right. So we know f equals k m1 m2 over x squared, but what do we know right now?
X is 100.
X is 1,000, so squared. And what else do we know? And f is 5. So, okay, right. But the whole beauty is, well, watch what happens. So, so what do we do? Well, 1,000 squared is 1,000,000. So what you get is, that's fine. Okay. 5,000,000 equals k m1 m2. And that's all we need. All we need to know is that 5,000,000 is the number on top. So we now know that force equals 5,000,000 over x squared. And the reason we know that is that k is some constant, it's not changing. m1 is some constant, it's not changing. m2 is some constant, it's not changing. Multiply them all together, you get a constant that's not changing. And that number is 5,000,000.
What is this step called when you equal the two terms on each side?
Equaling two terms. Okay. So now we know what the force function is. So now we can go back to doing what we need to do, which is finding work. And to find the work, we take the integral of the force. So in this case, we're finding the work, we're going from where to where? From what value to what value?
From 1,000 to 5,000.
From 1,000 to 5,000. So on the one hand, it's this. And on the other hand, it's this, and the force function was x squared dx. And then you just do that. Okay. And so let's finish solving this out. So to take this integral, what do we do?
Take out the 5,000,000, make x squared to negative x squared.
Right. So a nice way to deal with this is just realize that 5,000 is a constant you're multiplying by. So you can just think of this as 5,000,000 times that, and then x squared in the denominator is just x to the negative 2. Okay. And so now I'm still writing integral. I did not integrate yet. So far I just rewrote it. Okay. So now we've got 5 million times what's the integral of that? Yeah. And we want to do this from 1,000 to 5,000. Lots of zeros here. Keep track. Okay. So this is 5 million times, let's see, negative 1 over 5,000 minus negative 1 over 1,000. Okay. So this is negative 5 million over 5,000. Going to be negative 1,000 minus minus is going to give me plus, and that's going to be 5,000. So work it all out. You get 4,000. 4,000 what?
Joules.
Right. We're measuring work, so this is joules. So another way, particularly for the physicists, another way to think about this problem is to say that we are let me see. There's two objects. Okay. So initially the two objects have an energy due to the gravitation. They have an initial energy of 1,000 joules, and then by moving them apart, you bring them to 5,000 joules. So how much work did you have to do to make that change? 4,000 joules. So for the physicists in the house, this is really a discussion about potential energy. That's where the energy has gone. If you don't know physics, don't worry about that.
Okay, so there was this guy named Newton.
Yeah.
On how you approach the problem. What if you just take the integral instead of plugging in? Because I always do like the plugging in stuff at the very end. But if you took the integral of the law of gravitation, how would you do it?
Well, that's correct, but the issue is, so you start with just F equals Km1m2 over x squared. You're starting with that law for force. Okay, great. The problem is, if you start doing the integral directly, you don't know Km1, m2, so you're not going to get a number answer. You're going to get an answer in terms of Km1, m2, which is fine if you know K and m1 and m2. But what was the thing that we had to do as the other step? We had to figure out what it was. Does that answer your question? Yeah. Okay. So let me make a comment about something that may or may not confuse people, especially who don't have a lot of experience with physics. In physics, there are lots of general rules that says if you're in this kind of situation, here's the rule for all those situations. So I just showed you two. Law of gravitation, anytime you have two objects with mass, they exert an acceleration on each other. Hooke's law for springs. There's a rule about how the spring is going to move and the force it's going to exert. Okay. Thing is that not all springs are identical. And when you have two objects, not all objects are identical. They have different masses. So the way physicists deal with those situations is they just put constants in there. So with the spring, they say every spring has its own value for K, and we'll worry about that when we get there. The thing is, well, we're there now. So one of the things you want to do in an actual situation is the first thing you have to say is, well, okay, what is the K for this spring? And you have to do that before you do anything else, if you're in an applied situation. Now, obviously, you could just treat this like a theoretical physicist and say, I'm going to calculate everything and I'm just going to leave the constants there. And that's where you get all these crazy, ridiculous physics equations from with like 17 different constants in them. Because no one ever bothered to say, oh, and the value of the constant is 2 or whatever. All right. So in this class, generally, we're not going to do that. You could, but that's not the sort of thing that we're going to focus on. So the thing we're going to focus on is saying, I've got an equation. It's got some constants in it. But because I know some things, I can figure out the value of those constants. So for example, in the case of the spring, we said, oh, okay, well in the first case, I just told you the K. Someone else did the work and told us. Great. In the second case, I said, there are things that we can measure that can tell us the value of the constant. All right. So now notice this is the kind of constant that you get from a physics equation. You also get there's also constants that you get from the constant of integration. Both constants, but they come up for a different reason. So in physics, if you have a constant and you want to figure out what it is, there's some fact that you can use to find it. So for example, the fact was you have a force of 30 joules when it's at 6 meters, therefore you can find K. When we do an integration and we get a constant, you can solve for the constant using some fact, and that kind of fact has a name. What do we call that kind of fact? An initial condition. Okay. So this kind of fact that's on the screen, that's on the board right now, is a fact to help you find the physics constant. When we talk about integration, we say an initial condition helps us find the constant of integration. So, constants. Okay. And we're doing physics. All right. Any other questions? All right. So a quick, excuse me, a quick summary just to remind you of the main point of all these applications. The main point of all the applications is the following thing. We have two things that we measure or talk about, and one of them is the derivative of the other one. Now, we talked about this in a couple different contexts. We talked about this in the context, yes. We talked about this in the context of motion. If you have position, the derivative of position is velocity. We also know one more fun thing, the derivative of velocity is acceleration. We talked about this in the context of economics. If you have a cost function, the derivative of the cost function is what's something called the marginal cost. In electricity, if you're measuring an amount of charge, the rate for that is called the current. And again, rate is basically the same thing as saying derivative. And now we've talked about work. So in the situation of work, there are two things that we measure. One thing is work, which can be measured in like energy or joules. And the other thing is the force, which is basically work per distance. So in the sense of work per distance, joules per distance, force is the derivative of work. So once you know that you have a function and its derivative, we can do two things. In Calc 1, you said, well, if I have the original function, I can take its derivative and then find the other thing. Okay, great. Now we're in Calc 2. And what did we learn? If you know the derivative, take the integral, and that will give you the original thing you're trying to measure. But it's more subtle than that. Because we can talk not just about the original thing, which in this case is work. We can talk about how much work is done between 2 points, between two values. And that's what's tricky about the fundamental theorem of calculus. Is that it says we're not specific. We can not just recover the original function. We're actually going to say what's the change in the value of that function from this point to this point. Once you get that, you basically get it. Okay. So that's that.